What I want to do in this video is make sure that we're good at picking out what the normal vector to a plane is if we are given the equation for a plane. So to understand that, let's just start off with some plane here. Let's just start off. So this is a plane. I'm drawing part of it. Obviously, it keeps going in every direction. So let's say that that is our plane. And let's say that this is a normal vector to the plane. So that is our normal vector to the plane. It's given by AI plus BJ plus CK. So that is a normal vector to the plane. And let's say that we have, so it's perpendicular. It's perpendicular to every other vector that's on the plane. And let's say we have some point on the plane. We have some point. It's the point x sub p. I'll say p for plane. So it's a point on the plane. xp, yp, zp. If we pick the origin, so let's say that our axes are here. So let me draw our coordinate axes. So let's say our coordinate axes look like that. This is our z-axis. This is, let's say that's our y-axis. And let's say that this is our x-axis. Let's say this is our x-axis coming out like this. This is our x-axis. You could specify this as a position vector. There's a position vector. Let me draw it like this. Let me draw it like this. Then it would be behind the plane right over there. You have a position vector. That position vector would be xpi plus ypj plus zpk. It specifies this coordinate right here that sits on the plane. Let me just call that something. Let me call that position vector, I don't know. Let me call that p. Let me call that p1. So this is a point on the plane. So it's p. It is p1, and it is equal to this. Now, we could take another point on the plane. Let's say we're taking, this is a particular point on the plane. Let's say we just say any other point on the plane, x, y, z. But we're saying that x, y, z sits on the plane. So let's say we take this point right over here, x, y, z. That clearly, same logic, can be specified by another position vector. We could have a position vector that looks like this, and dotted line. It's going under the plane right over here. And this position vector, I don't know, let me just call it p instead of that particular, that p1. This would just be xi plus yj plus zk. Now, the whole reason why I did this setup is because I want to find, given some particular point that I know is on the plane and any other x, y, z that is on the plane, I can construct a vector that is definitely on the plane. And we've done this before when we try to figure out what the equations of a plane are. A vector that's definitely on the plane is going to be the difference of these two vectors. And I'll do that in blue. So if you take the yellow vector minus the green vector, or you take this position, or you will get the vector that, if you view it that way, that connects this point and that point, although you can shift the vector. But you'll get a vector that definitely lies along the plane, even if you, so if you start one of these points, it'll definitely lie along the plane. So the vector will look like this. And it would be lying along our plane. So this vector lies along our plane. That vector is p minus p1. This is the vector p minus p1. It's this position vector minus that position vector gives you this one. Or another way to view it is this green position vector plus this blue vector that sits on the plane will clearly equal this yellow vector, right? Heads to tails. It clearly equals it. And the whole reason why I did that is that we can now take the dot product between this blue thing and this magenta thing, and we've done it before, and they have to be equal to 0, because this lies on the plane. This is perpendicular to everything that sits on the plane, and it equals 0, and so we will get the equation for the plane. But before I do that, let me make sure we know what the components of this blue vector are. So p minus p1, that's the blue vector. You're just going to subtract each of the components. So it's going to be x minus xp. It's going to be x minus xpi plus y minus ypj plus z minus zpk. And we just said this is in the plane, and right, the normal vector is normal to the plane. You take their dot product is going to be equal to 0. So n dot this vector is going to be equal to 0, but it's also equal to this a times this expression. I'll do it right over here. So find some good colors. So a times that which is ax minus axp plus b times that. So that is plus by minus byp. And then let me make sure I have enough colors. And then it's going to be plus that times that. So that's plus cz minus czp. And all of this is equal to 0. Now, what I'm going to do is I'm going to rewrite this. So we have all of these terms. I'm looking for right color. We have all of the x terms, ax. And remember, this is any x that's on the plane will satisfy this. So ax, by, and cz. Let me leave that on the right-hand side. So we have ax plus by plus cz is equal to, and what I want to do is I'm going to subtract each of these from both sides. Or in other ways, I'm going to move them all over. Let me not do too many things. I'm going to move them over to the left-hand side. So I'm going to add positive axp to both sides. That's the equivalent of subtracting negative axp. So this is going to be positive axp. And then we're going to have positive byp plus, do that same green, plus byp. And then finally plus czp. Plus czp is going to be equal to that. Now, the whole reason why I did this, and I've done this in previous videos where we're trying to find the formula or we're trying to find the equation of a plane, is now we said, hey, if you have a normal vector and if you're given a point on the plane, where it's, in this case it's xp, yp, zp, we now have a very quick way of figuring out the equation. But I want to go the other way. I want you to be able to, if I were to give you a equation for a plane, where I were to say ax plus by plus cz is equal to d. So this is the general equation for a plane. If I were to give you this, I want you to be able to figure out the normal vector very quickly. So how could you do that? Well, this ax plus by plus cz is completely analogous to this part right up over here. Let me rewrite this over here so it becomes clear. This part is ax plus by plus cz is equal to all of this stuff on the right-hand side. Or sorry, on the left-hand side. So let me copy and paste it. Copy and paste it. So I just essentially flipped this expression. But now you see all of this a has to be this a has to be this a, this b has to be this b, this c has to be this thing, and then the d is all of this. And this is just going to be a number. This is just going to be a number, assuming that you knew what the normal vector is, what your a, b's, and c's are, and you know a particular value. So this is what d is. So this is how you can get the equation for a plane. Now, if I were to give you an equation for a plane, what is the normal vector? Well, we just saw the normal vector. This a corresponds to that a, this b corresponds to that b, that c corresponds to that c. The normal vector to this plane we started off with has the components a, b, and c. So if you're given equation for a plane here, the normal vector to this plane right over here is going to be ai plus bj plus ck. So it's a very easy thing to do. If I were to give you the equation of a plane, let me give you a particular example. If I were to tell you that I have some plane in 3 dimensions, let's say it's -3, although it'll work for more dimensions. Let's say I have -3x plus square root of 2y. Let me put it this way, minus, or let's say plus 7z is equal to pi. So you have this crazy, I mean, it's not crazy, it's just a plane in 3 dimensions. And I say, what is a normal vector to this plane? You literally can just pick out these coefficients, and you say a normal vector to this plane is -3i plus square root of 2 plus square root of 2j plus 7k. And you can ignore the d part there. And the reason why you can ignore that is that'll just shift the plane, but it won't fundamentally change how the plane is tilted. So a normal vector to this normal vector will also be normal if this was e, or if this was 100. It would be normal to all of those planes, because all of those planes are just shifted, but they all have the same inclination, so they would all kind of point in the same direction, and so their normal vectors would point in the same direction. So hopefully you found that vaguely useful. We'll now build on this to find the distance between any point in 3 dimensions and some plane, the shortest distance that we can get to that plane.